everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss a few numericals based on the concept of laser. Before we go to do the numericals, we'll have a quick recap of the formulae that we are going to use. So, the first formula we are going to see is E is equal to h nu, where E here represents the energy of the photon, H represents the Planck's constant, whose value is a constant which is 6.625 into 10 power minus 34 joules seconds. In most of the numericals, the value of H, the Planck's constant, will be given. If it is not given, you may have to remember it is approximately taken as 6.6 or 6.625 into 10 power minus 34 joule second, and nu here represents the frequency. Nu is the frequency of the incident photon. Now, if the frequency is not given and lambda is given, we know since nu is equal to C upon lambda, we can write this energy as E is equal to hc upon lambda. Means, knowing the wavelength of the radiation, the energy of the photon can be calculated. So, lambda here represents the wavelength. Next one is the formula for population, which is given by Boltzmann, and it is called as the Boltzmann distribution formula. So, N is given by exponential minus E upon kT. So, this is the formula for population. So, N here represents the population. Population here means the number of atoms that are present in a given state. We are calling it as population. So, population depends upon E, which is the energy. K here is the Boltzmann constant. We may also write it as Kb. In some books, it will be mentioned as Kb. K or Kb both mean the same, and it represents the Boltzmann constant. And the value of the constant is 1.38 into 10 power minus 23 joules per Kelvin. So, this is the value of T. So, we know E is the energy, Kb is the Boltzmann constant, and T is the temperature. Then we can find the ratio of the population. If you have to find the ratio of population between two states, N2 and N1. N1 is the population in the first energy level, N2 is the population in the second energy level. So, how do we get N2 by N1? So, we know N is equal to exponential minus E upon kBT. So, N1 will be equal to exponential minus E1 by kBT. N2 will be equal to exponential minus E2 by kBT. If we want the ratio, we also have N naught. N is equal to N naught exponential minus E upon kBT, where we talk about N naught with respect to the population in the ground state. So, you have N naught exponential minus E2 by kBT. So, how do we write N2 by N1? So when we write N2 by N1, you have N0 exponential. In the denominator also you have N0 which gets cancelled, and this will be minus E2 minus E1 by kVt. So we are taking it as a common. So E2 minus of E2 minus E1 upon kVt. So whenever we have to calculate the ratio of population between two states, we will not have N1, we will not have N0, because N0 is getting cancelled when we are taking the ratio. So N2 by N1 is equal to exponential minus E2 minus E1 in brackets upon kVt. So E1 and E2 are understood, energy of the first level, energy of the second level. Then the next formula for divergence, theta, is equal to A2 minus A1 upon 2 into D2 minus D1. Here theta represents the divergence of the laser beam. A1 and A2 represents the diameter of the spots that are formed due to laser beam. They are the diameter of the spots that are formed due to laser beam. D1 and D2 are the distances between the laser source and screen. Then the formula for the number of photons that are emitted. So whenever we are talking about a laser beam, it is all about emission, stimulated emission, where a number of photons are emitted. So to calculate the number of photons that are emitted, so what is the formula we are going to use is the total energy emitted. Total energy emitted upon energy of each photon. Energy of each photon. So if you know the number of photons, you can calculate the energy of photon also. So knowing the energy, you can calculate the photons. Or if you have to calculate the number of photons, we use total energy upon energy of each photon. Then one more formula to find the ratio of spontaneous emission to stimulated emission. This is given by exponential h nu by kT minus 1. So with the help of these formulae, now we'll be doing the numericals. First one, calculate the wavelength of emitted radiation from a semiconductor diode laser which has a band gap of 1.44 electron volt. So this is the first problem. So we are going to understand what a band gap is and how radiation is emitted, and then we will move on to calculate the wavelength. So when we try to draw the energy band diagram, we have a valence band. This is the valence band and this is the conduction band. And the lowermost level of the conduction band we denote it by EC, and the topmost level of the valence band we denote it by EV. And this region between EC and EV, we call it as energy gap. EG is equal to EC minus EV. So now what is given here is the band gap is given. And when a radiation is emitted in a semiconductor diode laser, semiconductor diode laser is a PN junction diode laser. So in a PN junction diode laser, we talk about a direct band gap. So where the k vectors of the valence band and the conduction band will match with each other, and when the radiation is emitted, you can calculate the wavelength of the emitted radiation. So now when we have to calculate the wavelength, we need to know the energy gap. So the energy gap gives us the energy of the radiation that is emitted. So let us write the data. So band gap is given, Eg is equal to 1.44 electron volt. So since the energy has to be expressed in joules, it is given in electron volt, we need to do the conversion. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So we will write it as 1.44 into 1.6 into 10 power minus 19 joules is the energy gap. What we have to calculate is the wavelength lambda. So which formula we are going to use now? We have energy Eg is equal to h nu. And since we have to find lambda, the wavelength, we will write nu in terms of lambda. So that will be hc upon lambda. Because since nu is equal to c upon lambda. Nu is the frequency, c is the velocity of light, and lambda is the wavelength. So Eg will be equal to hc upon lambda. We know the value of Eg. H is a constant, C is a constant. So what is the value of H? 6.625 into 10 to the power of minus 34 joule seconds. And the velocity of light C is given by 3 into 10 power 8 meter per second. So let us substitute these values in the formula. Eg is equal to hc by lambda, implies lambda will be equal to hc upon Eg. So we will use this formula now and do the substitution. So lambda is equal to h is 6.625 into 10 power minus 34. 6.625 into 10 power minus 34 into c, the velocity of light is 3 into 10 power 8 upon Eg. Eg is the band gap energy which we have converted into joules. So it is 1.44 into 1.6 into 10 power minus 19. So what we get here is 8626 into 10 power minus 10 meters. And we know that 1 angstrom is equal to 10 power minus 10 meters. So therefore we write it as 8626 angstrom. So the wavelength of the radiation that is emitted is 8626 angstrom. Now coming to the second one. A semiconductor diode laser has a wavelength of 1.55 micrometer. Find the band gap in electron volt. It is exactly the mirror image of the last problem. In the last problem, we are given the band gap and we have to find the wavelength. Here, the wavelength of the laser that is emitted by the semiconductor diode is given and we have to find the band gap. So, what is the data given? First, we will write. Lambda is equal to 1.55 micrometer. Micro here, 1 micro means what? 1 micrometer is equal to 10 power minus 6 meter. So 1.55 into 10 power minus 6 meter is the wavelength. What you have to find is the band gap is equal to how much in electron volt. So we need to have the conversion from joules to electron volt also. We know 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. So when we have to convert joules to electron volt, so 1 joule will be equal to 1 upon 1.6 into 10 power minus 19 electron volt. So this is how we use the conversion. So coming to the formula. We use the basic formula Eg is equal to h nu, that is equal to h c upon lambda. So we have the values here directly. The value of h is a constant, Planck's constant, 6.625 into 10 power minus 34 joule seconds. And the value of c, the velocity of light, 3 into 10 power 8 meter per second. So substitute the values here. 6.625 into 10 power minus 34 into 3 into 10 power 8 upon 1.55 into 10 power minus 6. So when you simplify, what we get here is 12.82 into 10 power minus 20 joules. We are getting the answer, the energy in joules. But we have to express the band gap in electron volt. So we will use this conversion we have seen here. So energy gap in electron volt, what we do here is 12.82 into 10 power minus 20 divided by 1.6 into 10 power minus 90. So we get it as 0.80125 electron volt. So the band gap is given by 0.8. We can write approximately 0.8 electron volt. Now coming to the third one. Calculate the wavelength of the emitted radiation from a semiconductor diode laser which has a band gap of 1.68 electron volt. We have to find the wavelength. Similar problem, only thing is the numbers are different now. So let us calculate. First write the data given. In the data we have the band gap. Eg is equal to 1.68 electron volt. And we have to calculate the wavelength lambda. First we convert this electron volt into joules. Energy always expressed in joules. 1.6 into 10 power minus 19 joules. Then we use the formula. We will first write the basic formula. Eg is equal to h nu or hc by lambda. This implies lambda will be equal to hc upon Eg, where the value of h is given by 6.625 into 10 power minus 34 joule seconds, and the value of c is given by 3 into 10 power 8 meter per second. So let us do the substitution. Lambda is equal to 6.625 into 10 power minus 34 into 3 into 10 power 8 divided by 1.68, the value of Eg we have tried. 1.68 into 1.6 into 10 power minus 90. So that gives us 7.39 into 10 power minus 7 meters. So the wavelength is given by 7.39 into 10 power minus 7 meter. If you have to express this wavelength in angstrom, because the wavelength is generally expressed in angstrom, and we know the conversion, 1 angstrom is equal to 10 power minus 10 meters. So how do we write it as 10 power minus 10? So I'll be shifting the decimal place, 3 places I can shift the decimal and write 7390 into 10 power minus 3, because I have shifted 3 decimal places and we have 10 power minus 7. I'm just explaining you how to convert it into angstrom. So after shifting the decimal place, we get 10 power minus 3. We already have 10 power minus 7. So 10 power minus 3 into 10 power minus 7, a power m into a power n is equal to a power m plus n, basic formula. So this will be 7390 into 10 power minus 10 meter. And 10 power minus 10 meter is 1 angstrom. So we can simply write it as 7390 angstrom. So the wavelength is expressed in angstroms as 7390 angstroms. Now one more. A semiconductor diode laser has a wavelength of 1.42 micrometer. Find its band gap in electron volt. First write the data. Lambda is equal to 1.42 micrometer. Micrometer we have to convert into meter because we'll be doing the entire numerical in SI system. So we need to convert this to meter. So 1.42 into 10 power minus 6 meter is the value of lambda, and we have to find Eg. Eg we have to find and also express it in electron volt. So we will write down the conversion here. 1 electron volt is 1.6 into 10 power minus 19 joules. And the value of H is 6.625 into 10 power minus 34 joule seconds. And the value of C, constant, velocity of light, is 3 into 10 power 8 meter per second. So we'll use all this, write the formula. Eg is equal to h nu or hc by lambda. Means because we don't know nu, we will write the value of nu in terms of known values, that is in terms of wavelength lambda. So Eg is equal to hc upon lambda. Just substitute the value of h, value of c, and also the value of lambda, which we have converted it into meters. So 6.625 into 10 power minus 34 is the value of h. C is 3 into 10 power 8 upon lambda 1.42 into 10 power minus 6. So when we simplify, what we get here is the energy, and to convert it into electron volt, because we are asked to convert the band gap in electron volt, we will simply divide it with 1.6 into 10 power minus 19, because 1 electron volt is equal to 1.6 into 10 power minus 19 joules. And when we have to express joules in electron volt, we will simply divide it with 1.6 into 10 power minus 19. So dividing with 1.6 into 10 power minus 19 gives us the value of energy in electron volt, that will be 0.874 electron volt. So the band gap is given by 0.874 electron volt. Now the next one. Find the relative population of the two states in a ruby laser that produces a light beam of wavelength 6943 angstrom at 300 Kelvin. So we are talking about a ruby laser that emits wavelength, and the wavelength that is emitted here is 6943 angstrom and at a temperature of 300 Kelvin. So what we need to calculate is the relative population. So we'll first write the data, write the formula, understand, and then do it. So what is the data given first? We are given the wavelength, the lambda, 6943 angstrom. And then we are given the temperature, 300 Kelvin. What we have to find is the relative population, that is N2 by N1 we have to find. So what is the formula we have for the relative population? We have already seen in the beginning how to get the formula for the relative population. N2 by N1 is equal to exponential minus E2 minus K1, minus of E2 minus E1 upon KBT. So this is the formula for relative population. So we have T, KB is a constant, the Boltzmann constant, 1.38 into 10 power minus 23 joules per Kelvin. T is given. E2 minus E1 we have to find. So how do we get the difference in energy? The formula for E2 minus E1, we will write it as h nu. And since we don't have the frequency, we have the wavelength, we will write it in terms of wavelength. H nu is equal to hc by lambda. And the value of c is the velocity of light, 3 into 10 power 8 meter per second is the value of c. Now, first we will find E2 minus E1. So, E2 minus E1 will be equal to 6.625 into 10 power minus 34 into 3 into 10 power 8 h into c upon lambda. Lambda is 6943 angstrom. And we know 1 angstrom is equal to 10 power minus 10 meter. So we will convert this wavelength into meters. So 6943 into 10 power minus 10 meter. Everything is in SI system. So we will write the wavelength also in meters. So we get E2 minus E1 will be equal to 2.85 into 10 power minus 19 joules. So you can use your calci to simplify this value and you get it as 2.85 into 10 power minus 19 joules. Now how do we get N2 by N1? N2 by N1 will be equal to exponential minus, you see, I'll write a square bracket, exponential minus E2 minus E1. What is the value of E2 minus E1? We got 2.85 into 10 power minus 19 divided by KT or KBT. 1.38 into 10 power minus 23 into temperature is 300. So when you simplify this, 2.85 into 10 power minus 19 by 1.38 into 10 power minus 23 into 100, when we simplify, we get it as minus 69.3. So that gives us the value of 8 into 10 power minus 31. So the ratio or the relative population is given by 8 into 10 power minus 31. Now coming to the next one. For a helium neon laser at 1 meter and 2 meter distances from the laser, the output beam spot diameters are 4 millimeter and 6 millimeter respectively. Calculate the divergence. So let us write the data. First we'll understand what is the concept here, and then we'll write the data and then formula and then simplify. So we have a helium neon laser. Suppose this is the source of laser. This is the helium neon source. So the light is emitted from this laser, and when it strikes the screen. So what is given for a helium neon laser at 1 meter distance? The spot diameter will be 4. So when we are talking about the distance between the source and the screen, this is the screen. Distance between the source and the screen here is 1 meter. So the diameter of the spot that is formed is 4 millimeters. Okay. And now when the distance is 2 meters, same thing we change. So if you are changing the distance to a scale, helium neon laser, which is the source, when the distance is increased, means now the distance between the source and the screen is 2 meters. Now the diameter of the spot that is formed is 6 millimeters. This is what we are given. So what you have to calculate is the divergence. Actually, when we talk about divergence, this is how the beam is diverging. That is how you get the spot, how the beam diverges. This is how you look at the divergence. So as the distance increases, the divergence is increasing. So now let us do the numerical. So we'll write the data. We will write the distances as D1 is equal to 1 meter, D2 is equal to 2 meter, and the spot diameters, I'll write it in terms of A1, 4 millimeter, and A2, 6 millimeter. Okay, D1, D2, A1, A2. These are the distances, D1 and D2. Distance between the source and the screen. A1 and A2 are the diameters of the spots that are formed due to the laser beam. Now we have to write the formula for divergence. We have already discussed this formula for divergence. Theta is equal to A2 minus A1 upon 2 into D2 minus D1. Now this is in meter and this is in millimeter. We need to convert this into meter. So 4 millimeter will be equal to 4 into 10 power minus 3 meters. 6 millimeter will be equal to 6 into 10 power minus 3 meter. Now substitute A2 minus A1 will be 6 minus 4 into 10 power minus 3 divided by 2 into D2 minus D1, 2 minus 1. So theta is equal to 6 minus 4 is 2 into 10 power minus 3 divided by 2 into 2 minus 1 is 1. 2 and 2 will get cancelled. We are left only with 10 power minus 3. So theta is equal to 10 power minus 3 radian, or we can also write it as 1 milliradian. The divergence here is only 1 milliradian because 1 milli is equal to 10 power minus 3. This is the conversion we have. 1 milli is 10 power minus 3. So when we are getting 10 power minus 3 radian as the divergence, so that is nothing but 1 milliradian. The next one, a helium neon laser emits light at a wavelength of 632.8 nanometer and has an output power of 2.3 milliwatts. How many photons are emitted in each minute by this laser when operating? So we are talking about a helium neon laser that emits light of wavelength 632.8 nanometer. And the output power of this laser is 2.3 milliwatts. We have to find how many photons are being emitted per minute. That is also important. So write the data. First, wavelength is given, lambda is 632.8 nanometer. Nano here represents 10 power minus 9 meter. We will convert it into SI system. Everything we'll write in SI. 632.8 into 10 power minus 9 meter. Nano means 10 power minus 9. And the power output is given as 2.3 milliwatts. Means we can write it as 2.3 into 10 power minus 3 watts. So what we have to find is the number of photons emitted. We have to calculate the number of photons emitted. So what is the formula for the number of photons emitted? Let us write the formula. Number of photons emitted will be equal to total energy output upon energy of each photon. Energy of each photon. So we will calculate first the total energy output, then we will calculate the energy of each photon, substitute and get it. So how do we get the energy of the photon? E is equal to h nu. Nu is not given, lambda is given. So we will use hc upon lambda and get the energy. So otherwise we will first find the frequency nu is equal to c by lambda. C is what? 3 into 10 power minus 8. Sorry. Velocity of light 3 into 10 power 8, not minus 8, plus 8. Upon lambda 632.8 into 10 power minus 9 is the wavelength. So we get nu as 4.74 into 10 to the power of 14 hertz. The frequency is expressed in hertz. So once we get nu, we can find the energy as h nu. H is a constant, the Planck's constant. 6.625 into 10 power minus 34 into 4.74 into 10 power 14. So this gives the energy as 3.14 into 10 power minus 19 joules is the energy. Energy of each photon. Now total energy output. So the power is given as 2.3 milliwatts. If we have to calculate the energy, let us go back to our basic formula. Power is equal to energy upon time. Energy emitted per unit time will give us the power. So if we want energy, it will be power into time. So the time here is we have to calculate it per minute, in each minute. So 2.3 into 10 power minus 3 into 60. 1 minute is 60 seconds. We will write it the time in seconds. So 2.3 into 10 power minus 3 into 60 is the total energy we can write. So let us substitute here. The total energy output will be 2.3 into 10 power minus 3 into 60 upon energy of each photon is 3.14 into 10 power minus 90. So this will be 4.3949 into 10 power 16 photons per minute. So the number of photons emitted per minute is given because they are asking how many photons are emitted in each minute. So 4.3945 into 10 power 16 photons per minute. Next, the ruby laser has two states at 300 Kelvin and 500 Kelvin. If it emits light of a 7000 angstrom, calculate the relative population. So we have already done one numerical on relative population, but here we'll be doing it for two different temperatures, and then we will compare how the emission varies with temperature. So write the data given. Wavelength lambda is 7000 angstrom. Temperature T1 is 300 Kelvin. T2 is 500 Kelvin. We have to find the relative population. Formula for relative population, N2 by N1 is equal to exponential minus of E2 minus E1 by KT. So K is a constant, the Boltzmann constant, 1.38 into 10 power minus 23 joules per Kelvin. And we have to find at two different temperatures. So let us first find E2 minus E1. So E2 minus E1 is equal to h nu or hc upon lambda. Because we are given the wavelength lambda, we are writing the formula for energy in terms of lambda. So E2 minus E1 is equal to h is a Planck's constant whose value is given by 6.625 into 10 power minus 34 seconds, joule seconds, and c is 3 into 10 power 8 upon lambda is 7000 angstrom. We will write it in terms of meter. 1 angstrom is 10 power minus 10 meters. So divided by 7000 into 10 power minus. This is the value of E2 minus E1. So let us substitute it here. Exponential minus 6.625 into 10 power minus 34 into 3 into 10 power 8 divided by 7000 into 10 power minus 10 into kb 1.38 into 10 power minus 23 into, for the first temperature we have 300. So exponential minus 6.625 into 10 power minus 34 into 3 into 10 power 8 by 7000 into 10 power minus 10 gives us the value of E2 minus E1, and 1.38 into 10 power minus 23 is K. And for the first temperature T is equal to 300 we are going to calculate. So we are getting 5.9 into 10 power minus 29. This is the value at 300 Kelvin. Now let us do the same thing for 500 Kelvin. If the temperature increases to 500 Kelvin. So the value of E2 minus E1 remains the same because it emits light of the same wavelength, 7000 angstrom. So how do we get N2 minus N1 at 500? Exponential minus 6.625 into 10 power minus 34 into 3 into 10 power 8 divided by 7000 into 10 power minus 10 into 1.38 into 10 power minus 23 into 500. Now we are doing with increase in temperature to 500 Kelvin. And then we get 1.4 into 10 power minus 16. This is at 500. So if you compare 5.9 into 10 power minus 29 at 300 Kelvin and 1.4 into 10 power minus 16 at 500. So as the temperature increases, the relative population is going to increase. Now the next one. Calculate the ratio of spontaneous to stimulated emission by an incandescent lamp at 200 Kelvin and nu is equal to 6 into 10 power minus 14 Hertz. Nu is given, temperature is given. We have to calculate the ratio of spontaneous to stimulated emission. So just let me explain the concept of spontaneous and stimulated emission. Now when we are talking about emission, we have two states, E1, E2. E1 here is the ground state. E2 is represents the energy of the excited state. When the atoms are in the ground state, we stimulate them with the help of some energy and we send them to the excited state. Means the atoms will make a transition to the excited state by pumping. This is with the help of a photon. Now, when the atoms which are in the excited state, they cannot stay there for a longer time. They will have to make a transition to the lower energy level, and the time for which they can stay here is very limited, which we call it as a lifetime. Once the lifetime is over, these atoms come to the ground state on their own and you call it as spontaneous emission. Spontaneous means on its own. If they are coming down, you call it as spontaneous emission, and the difference in energy is being emitted. E2 minus E1 is being emitted. Now, if we can stimulate these atoms, suppose we imagine that atoms are now in the excited state. Okay, they are in the excited state before the lifetime is over. If we can stimulate them with the help of an external photon, we get stimulated emission. What we get now is stimulated emission. This is the difference you need to understand, the concept of spontaneous and stimulated. Before the lifetime is over, we are stimulating them with the help of external photons to make a transition to the ground state. Then what happens? Along with the incident photon, you have the emitted photon, which is the difference in energy that gives rise to laser. What they are asking here to find is the ratio of spontaneous emission to stimulated emission by an incandescent lamp at 200 Kelvin, given the frequency is 6 into 10 power minus 14. So let us write the data and find the ratio. So data nu is equal to 6 into 10 power minus 14 Hertz. Temperature is 200 Kelvin. We have to find the ratio of spontaneous emission to stimulated emission. So what is the formula we have for spontaneous emission to stimulated emission? Exponential h nu by kT minus 1. This is the formula we have to find the ratio. I can write it as formula which we have to find also. Exponential h nu upon kt minus 1. H is a constant, 6.625 into 10 power minus 34 joule seconds. K is also a constant, 1.38 into 10 power minus 23 joules per Kelvin. Temperature is given, nu is given. So let us just substitute and get the value. So we have exponential h nu 6.625 into 10 power minus 34 into 6 into 10 power minus 14 upon 1.38 into 10 power minus 23 into 200 minus 1. So that gives us 1.7 into 10 power 6. So this is the ratio of spontaneous emission to stimulated emission. The ratio, it will not have any units because it's a ratio of two similar quantities. So the ratio is given by 1.7 into 10 power 6. Now let us do one more last problem. A pulse from laser with 1 milliwatt power lasts for 10 nanoseconds. If the number of photons emitted per second is 3.491 into 10 power 7, calculate the wavelength of laser. We have done a similar kind of problem. There we have calculated the number of photons. Here the number of photons that are emitted is given and we will have to calculate the wavelength of the laser. So write the data. So the power of the laser is given 1 milliwatt. Milli means 10 power minus 3. So 1 into 10 power minus 3 watts. And it lasts for 10 nanoseconds. So the time here is what? 10 nanosecond. Nano means 10 power minus 9 seconds. And the number of photons, capital N, the number of photons that are emitted is 3.491 into 10 power 7. Calculate the wavelength. We have to calculate the wavelength. So what is the formula we are going to use here? We have discussed in the formula in the beginning. So the number of photons emitted is total energy emitted upon energy of the photon. So now energy of each photon. Energy of each photon will be equal to total energy emitted upon number of photons that are emitted. Total energy upon number of photons. Actually here for us power is given. Power is equal to energy upon time. So if we want energy, energy will be power into time. So what will be the total energy here? Power 1 into 10 power minus 3 into time 10 into 10 power minus 9. So this gives the total energy upon the number of photons that are emitted. What are the number of photons emitted? 3.491 into 10 power 7 is the number of photons that are emitted. So this gives the energy of each photon. Now what we have to calculate is wavelength. We have the formula E is equal to h nu or hc by lambda. So if we have to get lambda, we write lambda as hc upon E. whatever energy we have got, we'll have to substitute here and we can get lambda. So lambda will be now equal to what? 6.625 into 10 power minus 34 into 3 into 10 power 8 divided by the energy 1 into 10 power minus 3 into 10 into 10 power minus 9, and this 3.491 goes to the numerator into 10 power 7. So that gives us the wavelength as 6942.6 into 10 power minus 10 meter, or you can simply write it as 6943 approximately angstrom. So what we have done here is to calculate the energy of each photon, we are first calculating the total energy emitted. So how do we get the total energy emitted? We are multiplying the energy with time, the power with time, you get the energy, upon the number of photons. Once you get the energy, we can calculate the wavelength using formula lambda is equal to hc upon A, and the wavelength is 6943 angstroms. Thank you. See you again with more numericals in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.